So we proceed with the second day of our excursion in the jungle of Hodge ideals and the spectrum. So it's a pleasure to introduce Professor Yoon, who is going to present to us his second lecture. Professor Yoon.
Thank you for introducing me again. Today I was late a bit because my laptop didn't start it, so sorry about that. Today I gave a third lecture on the paper. Here I'm gonna talk about something more on the spectrum, and then how to calculate in detail. So the first thing is last time I didn't give any definition of a spectrum, and of course so I didn't give any calculation method also. So today I'm gonna give such topics, and especially for isolated surface singularities. That's what we did in our theorem. So I'm gonna give another description on that, which is actually the same with that's the second talk of Seung-Jo. So all the time the setting is the same. We have an analytic function germ here. This is the review of last time. So from Cn to C, we have an analytic function germ at 0. This is a setting. Spectrum is one of the most important analytic invariant of hypersurface singularity of a function. Now, of course, you can think of that as it's a zero locus, but it tells them more. Actually, it's about the defining function. It has a lot of information of function and manifold, and the shape is that, like that. So that is a fractional power series. The important data was the coefficient of T beta and also the rational number beta, the pair of that. That includes information of monodromy and Hodge spectrum of a real number. So at this point, I should make some correction of last talk. In the last talk, we defined two more spectrum. The first spectrum is Steenbrink spectrum. The second one is Hodge ideal spectrum. The third one is Turing subspectrum. By the way, so these all these spectrums can be written as a non-decreasing sequence of power series. If F has an isolated singularity, right? So what I said last time, I said this sequence these sequences coincide until K is until Turing number from 1. That is a little bit wrong. Correct one is this. The sequence of Turing subalgebra is a subsequence of the other two. That is correct one. What is the difference? So since this sequence are non-decreasing one, the difference might happen in the middle of these sequences. the wrong by the wrong statement, only the last points are different. Okay. But what you can sure is the corrected one. Of course, our all the theorem in our the cases in our theorem is the first statement is correct. We cannot we haven't found any other cases. Yeah, first case, first remark was wrong so far. Anyhow, the theorem, what you can, the guaranteed statement is the second one. Any question? Okay, let me go to the next one. So I'm gonna show you the definition of here. I said the Hodge spectrum. That was in my thesis. But this is NF and Loses and also Saito thing. But Saito want to make a more clear, distinguishes all these spectrums. So maybe we should say this is the Steenbrink spectrum. Actually, the Hodge spectrum is order reversed. Okay, so that is defined by 1/Tn times spectrum. No, T to the n times spectrum of 1/F of 1/T. All right. So the data NF beta. This is given by alternating sum of a graded piece of F and of the lambda eigenspace of the reduced cohomology of Milnor fiber. Okay. Here the lambda comes from the monodromy action, and here the F is come from Hodge filtration. I'm gonna explain a bit more on that. I just leave yeah, you need to wait a few more minutes. Anyhow, we need some more background to understand our paper. I think maybe all of you already know that, but I'm gonna quickly review what the Newton polytope and non-degenerate and convenient cases. So here's an example. Instead of giving definition, I'm gonna show you an example which makes you maybe recall the definition. When you have a function f, polynomial function f, so for each terms you have a power. The first term has a monomial has a x to the 9 or x to the 5. So this pair 9, 5, we record we make a pair of these powers, and then that would be a set in Z2. We can choose a point corresponding on these pairs in R2 or Z2. And then we consider the first quadrant part plus each point. Okay, so for the point 0,9, you have this one. For the point 3,7, you have this area, and so on. And then finally we add them. We make a union of them, and then finally we take a convex whole of them. That is called Newton polytope, noted by gamma plus of f. That's a pink area. By actually, this is this area determined by only 3 points, right? So 4.2, 2.3, 0.9. So there are many polynomials giving the same Newton polytopes. For instance, like you only can choose these 3 points, these 3 monomers that gives the same Newton polytopes here. The previous example, the important thing is the boundary here. Especially, we can find the compact face. So face is points in here, points or line segment or array here. Compact means we do not count the array here in this case. So there are 0-dimensional face. We have 3 points here for the 0-dimensional face. 0,9, 2,3, 4,2. And we have a 1-dimensional face, A, B, B, C, C, A. So all these are the compact face. And then we define some related polynomial for each basis. So for instance, consider the base AB, that is 0,9 and 2,3. The related, the corresponding polynomial is the monomial, which has the same coefficient with the original one. So here, x squared, y cubed, it should have a coefficient 5 here. And y to the 9, oh, sorry about this. This should be plus. Okay. This is a typo. So this is our function f sigma. Newton boundary is a non-degenerate. The concept of non-degenerate is important here now for the calculation. That means for each base sigma, we gave a function, a polynomial f sigma. If f sigma has singularities only in the coordinate axis, then that we call that non-degenerate. So, for instance, f sigma in front of the previous example has this one, and we factor out y cubed. So the front one, so 5x squared minus y6 is has an isolated singularity at origin, and from the y cubed we have a y equals we have a singularity along y equals 0. All the singularities in coordinate axis, so it is non-degenerate. Here's another case which is not non-degenerate. So we have a polynomial. The same way, find the support and draw finding the basis of a Newton polytope. In this case, we have a 3 compact phase, 2 zero-dimensional, sigma 1, sigma 2, and 1 one-dimensional phase, sigma 3. For sigma 1, we have a f sigma 1, that is x squared y. It has a singularity along x-axis, so it is non-degenerate. For f sigma 2 also non-degenerate. F sigma 3, this is this can be factored like this: y times x plus y cubed, or y squared. So it has a singularity along x plus y equals 0, which is not in the coordinate axis. So it is not non-degenerate. The point is this: non-degeneracy is not the property of Newton polytope itself. It's rather determined by coefficient. So, for instance, if we change a coefficient here, instead of 2, the previous example we changed it 2 by 1, then that has the same Newton polytope, but it is non-degenerate. Another concept is convenient. So if there is a zero-dimensional phase, in this case, so on the axis, on each axis, we have when you have a zero-dimensional compact phase, that is convenient. So the left one is not convenient. We have a phase, compact phase on y-axis, which is a sigma 2, but we don't have a compact phase on x-axis. But the right-hand side, that is a convenient case. Both axes has a compact phase. So here's a remark. Newton polytope of F is non-degenerate and convenient. Then F has isolated singularity at origin. However, we cannot say the other way around. So we cannot say the converse. Even though we have a isolated singularity at origin, but we do not know if that is non-degenerate or convenient. However, good news is this: Newton, the non-degeneracy actually determined by non-degeneracy and convenience determined by coefficients. So those are very special, which means non-degenerate and convenient are generic for isolated singularities. All right, let's go to a description of a Milnor fiber and spectrum. I showed you the definition of spectrum. So to accomplish the definition of the spectrum, we need to explain what the Milnor fiber and monodromy and Hodge filtration is. Actually, the spectrum is given by Steenbrink, maybe the first. The first person introduced the spectrum is Steenbrink, I think. And he gave a spectrum for isolated singularities. The definition which I showed you, is a kind of a generalization of the definition. You already see the original spectrum of a Steenbrink last time. So after explaining the previous definition, I'm gonna show you why this is the same with the Steenbrink spectrum for isolated singularity. Here's the same setting. We have a function germ, but here I use the polynomial function germ because this is a theorem, also a definition, but also theorem to say the following statement, which is not true in analytic category as far as know, even though I do not have an example. Consider a very small neighborhood, small ball on both sides of a source and target. So we call B 0 epsilon for the source part, and the target part we pick delta delta, which is a small disk, but delta star is a punctured one, it's punctured at 0. And then we can restrict the function on the pre-image of the punctured disk intersect with a small ball on source Cn. Then our function f, the restricted function f, gives a locally trivial smooth vibration. That's a theorem. If the ball and disk are small enough. Locally trivial smooth vibration, which means each fiber are smooth and the fibers are diffeomorphic each other. That is called a Milnor number, a Milnor fiber, denoted by MF0. Here 0 is this function is a function germ at 0. We can find the invariant of singularity in terms of Milnor fiber. So all the invariant from the Milnor fiber will be an invariant of singularity. The cohomology of such an example is the cohomology. But we have more structure here, complex structure on Milnor fiber. So we can give a Hodge structure here. Here the Hodge structure is a Hodge filtration, actually. Originally the Hodge structure was given for a compact and smooth one, but Milnor fiber is not compact. Here the compact means an analytic category. So instead of so the Hodge structure is comes from historically actually many people know as a Hodge decomposition, but equivalent we can give a Hodge filtration. So there is a reason for that. To generalize the compact and smooth case to non-compact or non-smooth cases, we need a change of we need to use a filtration instead of decomposition. Anyhow, so we denote each graded piece by GRFP for each cohomology groups. That's this Hodge piece. All right. So we need the one more concept, monodromy, which is a monodromy. Consider a loop around zero on target space and lift that loop to original source manifold Cn, and then you can think of the flow, and the Milnor fiber moves along this loop, and then finally you return to the original one, but the map between these two, when you return to original Milnor fiber, that is not the same map. That is not identity map. So that is called monodromy. Topologists call this is a monodromy, but in algebraic geometers, we call geometric monodromy, which is denoted by H here. That might not be unique. However, if you think of the action induced by this geometric monodromy on cohomology, action on cohomology, that is unique. Okay, so we call that monodromy T. That is just a linear map. Now, we have two concepts, Hodge filtration and monodromy. So you can decompose the cohomology by eigenspaces, and also you can decompose cohomology by Hodge pieces. So the left here, the left hand side is Hodge piece of the lambda eigenspace, but the right hand side is a lambda eigenspace of this Hodge piece. Yeah, the fact is these are the same, so you don't need to think of a parallel space here. Okay. So the definition, let's see again our definition. So the data NF beta, that is given by dimension, alternating sum of dimension, graded piece of graded piece of lambda eigenspace of cohomology. Here this is a reduced cohomology of MF. You will see why we use a reduced case by example. And this is called vanishing cohomology. If you sometimes if you don't have a non-reduced one, then that's called nearby. Anyhow, so we know that all the notations here, and the point is the difference between the isolated cases alternating sum. That is this. This is given by actually in the second talk of by Seung-Jo showed this definition. This is only for isolated singularity. The difference is this alternating sum. This is kind of yeah, all the characteristic. So to generalize the spectrum is Euler characteristic of original Milnor fiber. The a bit difference is this. Usually the alternating sum start from 0. So for the 0th cohomology, we give a positive. So even part of cohomology, we give a positive, but negative has a negative. Odd part has a negative. But here, that is not true. The reason is this: to give n-1 part, to make the n-1 part positive. That's the reason. This is a little different. Anyhow, so for the isolated case, what happened? Okay, put number 1 into spectrum. So t equal 1 in case. Isolated case as becomes like this, the summation of the beta here, and this graded these pieces, the dimension of these pieces actually gives summing of all these pieces gives actually dimension of n-1 part of homology. That is a Milnor number. All right. Just for I think many of you know what a Milnor number is, but let me just remind you, review on the some to explain what the Milnor number is. So for the isolated singularity, Milnor proved that the Milnor number is a bucket of spheres. The sphere has dimension n-1. The number of spheres is called Milnor number. So that spheres is inside an n-1 cohomology. That is a Milnor number. So the dimension of that cohomology is a Milnor number. We call the number NF is a spectral number in this case, and that's spectral number. A spectral number is here's again a typo. This is spectral multiplicity. Sorry, this is spectral multiplicity and beta. Is defined as a piece of homologies n-1 homology, and actually that is a subquotient of this vector space. And summing up is gives, of course, summing all these things that gives a dimension of homology, n-1 homology. So for the isolated case, NF n beta can be spectral multiplicity cannot be negative because that's a dimension, and also when you summing all these numbers becomes a Milnor number. In other words, which means so when you have a Milnor number, we can express a spectrum by summing t to the beta I. Here we do not have a coefficient. All the coefficients are 1. So here the beta I is a number attached to each homology cycle, which means each sphere in bucket of sphere. So what the beta I is, that's another expression. This expression coincides actually with the sequence of non-decreasing sequence of rational number beta. On the other hand, we have we can calculate Milnor number by dimension of Jacobian ring, which is converging power series modulo Jacobi ideal, which is called sometimes a Milnor number. I'm gonna denote that JF. The reason for that is very related. That's related to the second talk of yesterday by Seung-Jo, because which is the relative. If you remember, actually I didn't not write here, but it's maybe you remember the Briscoe lattice and from the Briscoe lattice, how to calculate n-1 cohomology, the fiber. Then that is isomorphic to this Jacobi idea, a Jacobi ring. Right. So we could have another description for isolated singularities here. Isolated singularity. So that was defined by a piece of n-1 cohomology, but the dimension of n-1 cohomology correspond to Jacobian ring. So instead of making piece on cohomology, we could make a piece of Jacobi ring. That gives actually the V-filtration gives such a piece. So in fact, n beta is a beta graded piece of JF Jacobian idea. This is given by the isomorphism, which is given yesterday by Seung-Jo. Right. We give an example. This is the simplest example, one variable example. So f is x to the r. Then the Milnor fiber would be r points. So because x to the r equal 1 has a r solution. R points actually means bouquet of sphere. Here the sphere has a dimension 0. What is a zero dimensional sphere? That is 2 points, right? So when you make a bouquet, you attach you glue points on each sphere. When you glue these spheres at one point, then that would be what? That becomes r minus 1. R points is r minus 1 spheres. Bouquet of spheres. All right. So in fact, the dimension that is the same with the dimension of dimension of zero cohomology of Milnor fiber, because Milnor fiber is zero dimensional. Also, that is coincide with Hodge spectrum plugged in 1. Now, it's time to consider the monodromy on these R points. R points actually, so if you actually, you can make an exact map, a loop below. For instance, like e to the 2 pi I t I theta, something like that. And the action happens like this. So the first point go to second point in the middle fiber. Second point go to third point. So which makes a matrix on the zeroth cohomology. It is 0, 0, 0, 0, 0, 0, and finally 1, and 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, something like that. So then moves each point one by one. And then we are considering the reduced cohomology. We subtract one-dimensional guy. We have to subtract one-dimensional guy, which is a trivial action. So only considering the if you think of the eigenvalues here, you will have a 0. No, you will have a 1. That is e to the pi I 0, and then next one is e to the 2 pi I 1 over r, e to the 2 pi I 2 over r, something like that. So each subspace, each corresponding eigenspaces has a dimension 1. So our spectrum is given by t to the r 1 over r plus blah blah blah, increasing the numerate t to the r minus 1 over r, something like that. This can be written simply like this shape. So we got a formula for r x to the r cases. I didn't talk about the Hodge filtration here because zero-dimensional guy has the Hodge number is just 0. All everything's are 0, so we don't need to think about that. On the other hand, we could think of Jacobi idea. So differentiating f, we have Rx to the r minus 1. That has that is a ring, but also C vector spaces with a basis 1 x blah blah x to the r minus 1 cases. The overline here means a class of this in this quotient. Now, in the previous section slide, I said this gradient piece are the same with this gradient piece. So that is exactly correspond to this generator at k minus 1. Okay, see, be careful here. X to the k, that is not x to the k minus 1. You will see that why that happens. Yeah. Okay. And as I said, zeroth graded piece, the Hodge number is 0 because that is because all the Hodge piece of zero-dimensional guys are 0. In other words, from the formula, actually, we also have a 0 here because k it starts from 1 to r minus 1. All right, let's compute now. So far, we here I'm gonna introduce three methods. One is work for every hypersurface singularity, which is called Thom-Sebastiani formula. Another two is for isolated case singularity cases, for semi-weighted case and non-degenerate cases. The definition of semi-weighted is given yesterday. Actually, we want to calculate more, which you can, in the case that you cannot use Thom-Sebastiani formula. Another method is given by Steenbrink conjecture, which is proved by Saito. And that is, we can use calculate the spectrum. This method, which is of course is not it's very complicated in practice, but it works for only in single locus dimension 1 case. For the singular dimension 2 cases, there is a Nero and Budur and Saito made some kind of algorithm for homogeneous case, and I calculated the surface singularities in a certain kind of surface singularities, which has dimension, singularity dimension is 2. Also, I have calculated a 4-dimension reduced plane arrangement in four variables, which has singular dimension 2. These are all the results which has a kind of formula. So anyhow, let's start with the Thom-Sebastiani formula first. When you have two function germs, f and z, that has a different set of variables. In this case, we can calculate, if we calculate each of spectrums, then the spectrum of sum f plus g is multiplication of spectrums. In the case g is 0 constantly, in that case spectrum, we think that spectrum is negative t to the m. So actually this is good to make, by this we can calculate it we can calculate a non-isolated singularity case, because if we consider n plus m variable function germ, and it is written by only in n variables, and that bus which has isolated singularities, then the dimension of singular locus is n along the so that can be, we can use such a method also. All right, that works for everything. Here's an example. If f is x to the r, z is y to the s, then from the previous formula, we just multiply these two fractional power series, actually, which is equal to these fractions. So this x to the r plus y to the s is actually isolated weighted homogeneous singularity, with the weight 1 over R and 1 over S. So we can make a Fermat type polynomial. We can make a formula for Fermat type, just the multiplication of all these kind of styles, right? Let's see what happened in Newton boundary, Newton polytope. So consider the cusp case here. Jacobi ring is has two monomial bases, 1 and y. That is located and is a red dot as a red dot here. However, we can multiply x times xy for each generator. Then the 1 goes to 1, 1. Origin move to 1, 1. 0, 1, which correspond to y, move to 1, 2, which is x, which correspond to x, y squared. Moving these 2 points, we can put these 2 points into this rectangular, rather rectangular. Okay. The same phenomena happen to all these Fermat type. So from the Jacobi idea, we have a monomial basis. We move 1, 1, 1 for each point, which means multiplying x, y, z, x1, x2, xn. That makes all the points into exactly inside of the box generated by this basis. All right. So let's go to the formula for semi-weighted homogeneous polynomial. Actually, Seung-Jo, the second talk of the yesterday, we introduced already. Now, yeah, so I do not give a definition of that. I will not explain, but let me just remark a few things. Semi-weighted implies that the n-1 dimensional compact space is 1 or none. But the converse is not true in general because we need one more condition. F1 has isolated singularity. Okay. Also, another remark is this: weighted homogeneous polynomials in two variable, that is a non-degenerate. So you may confuse. Okay, all the weighted or semi-weighted homogeneous polynomial is non-degenerate? No, in general it's not. From the three variables, you could find this kind of examples. Of course, since the number of compact space n-1 dimensional compact space is 1 or none, so you cannot. That should have a isolated singularity. You cannot make that non-degenerate. But from the three-dimensional case, you have more phases, like in this case, line segment from 0, 0 and 0, 1, 1. So semi-weighted homogeneous and non-degenerate cases both are not equal to each other at all. Of course, many parts are shares, but so here's the formula of a semi-weighted homogeneous polynomial, which is the formula Seung-Jo shown before, but also I showed you with Fermat type polynomial case. That is exactly the same. All right, let's move to the non-degenerate convenient case. Sorry, I started a bit late. So can I use 2 or 3 minutes more?
Yes, you can.
Thank you. All right. For the non-degenerate convenient case, you have a formula by Steenbrink and Saito. Later theorem, I state a later theorem first. That is Saito theorem. If F has a non-degenerate and convenient Newton polytope, then spectrum is Poincare polynomial of graded ring of Jacobian ring. Here, the grading is given by Newton filtration. In other words, in this case, V filtration and Newton filtration is the same. All right. Then the question is, how to calculate the Poincare polynomial of this ring? So there is we need some notations on this graded ring. We have a Newton polytope, and we have a graded associated algebra generated by monomial in form of sigmas, and also that from that algebra we can calculate the Hilbert-Poincare series, and then we define another polynomial, which is given by 1 minus t to the d to the sigma d of sigma, and times Poincare polynomial with that graded ring. And then we need one more number, which means the k, which means the minimal number of containing sigma, minimal coordinate, the number of coordinate which contains sigma. All right. So the formula is given by this. We have to sum all the sigma. These terms for all the sigma. Here sigma includes the empty set also, and the whole every set. So, yeah, these two. From these two theorems, we have a formula for non-degenerate and convenient case. In practice, it's really complicated to calculate, but except two-dimensional cases. Here's the two-dimensional cases. So, okay, we have a polynomial here, and by the support and boundary, and here the red dots are correspond to the basis of the Jacobian ring, which is shifted. Okay, and if you observe this, the red dots are exactly inside of this each parallelogram or this line segment. So the if you see this line segment, it's inside it is doubled inside the correspond to the zero-dimensional faces. Inside the zero-dimensional faces inside of the first quadrant. So these are the basis of Jacobian ideas. So the middle number is a number of this point. And now, what is the question? We have a expression for, we just need to give on some numbers for each points here. This is another expression. So the number beta I, that is so to give such a number, we give a kind of a norm function L. So this function L gives a 0 at origin and gives a 1 the boundary of a Newton boundary and changes proportionally. Okay, then each point, this function gives for each point, right? So that is a beta. And then, yeah, that is another formula. Yeah, this method is actually very easy. Constructing looks like this picture is actually given by Arnold. We can generalize this method in higher dimension instead of using the formula given by Steenbrink. But this is not always applicable because we need a parallelogram. But in two-dimensional case, everything's a parallelogram or line segment. But in three-dimensional cases, yeah, there are n-1 dimensional face, which is not triangle in three-dimensional, right? So we cannot think of a parallelogram in that cases also. And moreover, so we could think of actually nowadays we make a formula for using this method, gamma spectrum, which is called a gamma spectrum. And even though we think of such a simplicial cases, the formula is not the same in general. Good news is in many cases coincide, and the error is not that much, even these two are different. The last okay, and the last remark, the theorem. Our theorem was this. Here, there's no convenient condition. Actually, we avoided the convenient condition. Okay, that's another point of our theorem. Thank you.
All right, let's thank Professor Yoon again. Any questions? So I have a question. Is there any hope to compute directly without using Thom-Sebastiani examples in dimension 3 or 4?
You mean the dimension 2 or 3 means the dimension of singular locus is 2 or 3, you mean, right?
Yeah. Let's say dimension 3.
That's for weighted for homogeneous case, there is an algorithm, maybe method or algorithm kind of, but it's really complicated. And the other cases, actually, I don't know. Maybe you could, in principle, it's possible because there is a motivic middle fiber formula, but the problem is again that is a summation of some simple pieces, but we do not know the spectrum of simple pieces. That is problem. So yeah, the things here which I stated here are the almost everything. Yeah, the formula.
Okay.
Yeah, these are the only formulas which I know.
Other questions?
So I have a question. So for dimension 3, for the three-dimensional polytopes in your other paper, there's these defective spectral numbers. Are these
Yes.
related in any way to the defects for the Hodge ideal spectral numbers? Did these line up in some cases, or is there any relationship between those two defects?
Oh, yeah. I haven't thought about that, but yeah, that's gonna. I think that has some relation. They might have a relation, but I don't know. Yeah,
Okay.
what that means, right?
All right.
Yeah,
Thank you.
that's the error of in the previous slide. Defect.
Other questions? All right. Thank you very much again.
Thank you.